Hi, my name is John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. This is part 4 of transformations of functions. So if you haven't already seen any of the earlier parts, I'm going to link those videos in the description box below. Please go ahead and take a look at them. Let's start. Dilation of a function from the y-axis is of the form y is equal to f of ax, all right? And we are going to consider the case where the absolute value of a is greater than 1 and when the absolute value of a is less than 1. For negative values, we'll take a look at it when we talk about reflections of functions, okay? So right now, we're just taking into consideration when the absolute value of a is greater than 1 or less than 1. But what's important is look at that a. All right, look at that a. It's affecting only the term inside f of x. Okay, that means it's affecting the domain. All right, affects the domain, not the range. All right, only the x values. Okay, but how would that affect the graph of a parent function? Let's say we had y is equal to x squared, my favorite quadratic parent function. How would the graph of a quadratic be affected or be transformed because of this ax? Okay, we said a is a factor, either being greater than 1, absolute value of a greater than 1, or the absolute value of a less than 1. How would that change in the domain? Because that's affecting the domain, as we saw. How would that transform the parent function? What would the transformed graph look like? Let's find out. Okay, so we go to the graphing calculator, and here let's add a graph page. And the first thing we do is we add y equals x squared as our parent function. Let's move the label away there. For the sake of convenience, I'm just going to adjust this, not like that. I want to remove this here. There you go. That's how I wanted that's the graph of y equals x squared, the parent. Now, let's add the transform function f1. Remember, f1 was our quadratic, okay, the parent quadratic. f1 of, we want ax. And this time, as absolute value of a greater than 1, let's take a value 2. Okay, 2 times x is what we're looking for, 2 times x. So that's the transformed function, transformed from the parent, okay, which was y equals x squared. Now, when you look at the graph, it looks like the red graph, the transformed graph, y equals f of 2x, all right? It looks like the graph has shrunk, okay? It's shrunk, but it's also looking like it is moving closer to the y-axis. And if you recall from the earlier video when we spoke about dilations from the x-axis, a graph moving to the x-axis or moving to the y-axis, this is moving to the y-axis. So if it's moving to the y-axis or it's moving to the x-axis, that doesn't say much. You need to really compare a point, okay? If you compare a point from the parent function and how has that point transformed in the transform function, that will give us a clear idea of what the transformation is, okay? So let's do that. And in order to do that, remember, it's only the x values, the domain that's undergoing the change and not the y values. So we'll take a constant value for both the functions, that is the parent function and the transform function. The constant value I'll take is y is equal to 4, okay? So there you go, that's y equals 4. And let me change the color of that so that it stands out a bit. So the color of that line, we are going to make it something like magenta. And those are the points. It's not very... let me zoom in so that it stands out a little bit. So Windows zoom, and I'm just going to say, let's do a box zoom around that area. There we go. Now we can compare. All these points have become something else. So that's all right. Let me see if I can change the setting here. I go to the home screen and change the document settings to approximate. That's good. I think we should be good now. And yes, we are good. Those have gone away. And we are interested in comparing. This is my transformed graph, and this is the parent graph. Okay, don't forget that. And we took this 4 so that it's a common y value for both the functions. And let's compare these 2 points, just these 2 points. Okay, how has that point on the blue graph transformed in the transformed graph? Okay, so to do that, let me just go and find the point, which is the intersection of the blue graph with this magenta graph. And we're just looking for this point, right? So let's get that point. That is 2, 4. 2, 4 on the parent graph. Let's see what's happened to it on the transform graph, on the red graph. So the point of intersection of the red graph and the magenta graph, that's the point, and it's become 1, 4. So 2, 4 becoming 1, 4. The y coordinate is not changing. It's the x coordinate that's getting transformed, okay? 2 becomes 1 when the transformation is y is equal to f1 of 2x. 2 becoming 1. 2 becoming 1. What is the transformation? Well, probably it's not clear. Let's investigate with another value. All right, let's just make this 2 into 3 and let's see what's going to happen to the same point. Okay, can we see that? Ready? Here we go. All right, so 2, the point 2 comma 4 in the original parent function has become 0.667. Okay, if you were to make a table of values and compare this, you'd know what's going on. So let me just explain that. If I add a calculator page and just observe, how did 2 become 0.667 as a result of 3? This was 3 times x inside the domain, right? So 2 divided by 3, let's see what's that answer. 0.667, and here we go. All right, 2 divided by that factor a greater than 1, is the new value for the x. Let's just check with some other value of a, right? So if I make this 4, then according to this method that I explained right now, the new x coordinate in the transform graph should be 2 divided by 4. Is that right? 2 divided by 4 should give me the new value for the x coordinate here for this new for this transform point. 2 divided by 4 is half. Let's just check what happens. Oh, the point just went away. So I don't know what happened. Let's just bring that point back again. Intersection of the transform graph and the magenta graph. That's the point we're looking for. And that is 0.5. That is half. Okay. So 2 divided by 4 gives us that new coordinate. Okay. So that means if the absolute value of a is greater than 1, then 2, whatever the x was, okay, we just took 2. So x divided by a would give the coordinate, the x coordinate of the new transform point. So don't just look at the fact that the graph is moving closer to the y-axis. Yes, it is happening, okay? So in a way, it is like saying 2, the value 2 became 0.5. It's almost shrunk. For the same point, 2, 4 became 0.5, 4. Why? Because the x value of that point has shrunk from the y-axis, okay? Shrunk from the y-axis. I said from the y-axis, okay? That word is important. Shrunk from the y-axis, almost like a compression from the y-axis. It's a dilation from the y-axis. So the point 2 has become 0.5 by a factor of 2 divided by a in this case, which is 4. Let's make a note of that quickly, okay? So what we saw was when the absolute value of a is greater than 1, the point with coordinates x and any k, the k is constant, all right? So k we took was 4. That point actually became x divided by a, comma k. The k remained constant. Remember, there was no change to the y values. It was only the x value that underwent a change, and the change was x divided by a. All right. Now let's find out what's going to happen when the absolute value of a is less than 1. Okay, let's take a value less than 1 and check on our calculator. So here we go. This was 4 right now. Let's make it 1/4. Okay, so I'm just going to make it 1/4 because 1/4 is less than 1. Okay, and we're still keeping it positive, remember? Okay, so I'm just going to enter that fraction again. I'm going to make it 1/4, and let's watch out for our point. It might disappear, but don't worry. We'll bring that point again. Okay, so 1/4, and here we go. And as we expected, it disappeared. But notice the graph. Earlier, when the value of a was greater than 1, it was moving closer to the y-axis. But now it's moving away from the y-axis, meaning it's moving closer to the x-axis. But like we said before, moving closer to the y-axis or moving closer to the x-axis, that really does not give a clear idea of what is happening to the point. Pick up some point, like we picked up 2, 4, and compare that x-coordinate, because it's the x-coordinate that's undergoing a change. It's the transformation of the domain. A dilation from the y-axis is a transformation of the domain. So let's compare this value. So I'm just going to move this graph here, and here we go. That's the point that's happened, okay? So a less than 1, first of all, first observation was that the graph is moving away from the y-axis or moving towards the x-axis, as you say. Let's find out this point, okay? So here we go, menu, analyze, intersection of this red graph with that magenta. That's the point we're looking for. And here we have 8, 4. So 8, 4 are the coordinates of the new, the transformed point. The original point was 2, 4. And if you were to compare 2 and 8 with this a is 1/4, it's the same factor, all right? 2 divided by 1/4, all right? Let's check it out, okay? 2 divided by 1/4. So if I were to write it like this, okay? So it's 2, all right? Divided by, remember right now the a is 1/4. So let me put a fraction here, okay? So 2 divided by 1/4, I should get 8. So when we saw that, when we saw f f1 of 3 times x, we noted that it was 2 divided by 3. And even now, when a is 1 by 4, we have still observed that 2 divided by 1 by 4 is 8. And that is the relationship, that the new x coordinate is actually the old x coordinate divided by that a that influences the domain. 2 divided by 1 by 4, that means x divided by a will give you the new value of x. And yes, the graph moves away from the y-axis, that's true, but this is more important. But what we can see is that when 2 becomes 8, it's a stretch. It's a stretching away from the y-axis. When a was greater than 1, we saw that it was shrinking, it was compressing towards the y-axis, okay? And this is a stretch from the y-axis by a factor of 1 by a. So let's note this thing down, that when the original point was x comma k, remember k is a constant, okay, because you're just interested in the changes in the domain, the x values. The change happened to be again x over a comma k. All right, remember a was less than 1. All right, so the only difference between absolute value of a greater than 1 and absolute value of a less than 1 is in the graph. What's happening? When the absolute value of a was greater than 1, we observed that there is a shrink, okay? The graph, let me write it here. Graph shrinks or is compressed by a factor of 1 by a, okay? A is greater than 1. When a is greater than 1, okay, as we saw, when a was 2 or 3, the shrink factor, the graph shrunk or was compressed by half or 1/3, depending upon the value of a. And when the absolute value of a is greater than 1, like this, sorry, less than 1, like this, there we saw that the graph stretches. The graph gets stretched by a factor of, again, 1 by a. Remember, a is less than 1. So when a was equal to 1 by 4, as you saw on the calculator, look at that. When a was 1 by 4, 1 by a would mean 4 times, right? 1 by a. 1 over 1 by 4 would be 4 times. That's why it's 2 divided by 1 by 4, giving you 8. So the stretch factor is 1 over a again, and so this is correct. So a dilation from the y-axis is either a shrink or a compression towards the y-axis of the x values. It's the transformation of the domain. The x values get shrunk or compressed by a factor of 1 by a. When the absolute value of a is greater than 1, the x values get shrunk or compressed by a factor of 1 by a. And when the absolute value of a is less than 1, the x values again get stretched by a factor of 1 by a. I hope that this video was useful to you. I'm going to see you all in the next video.